In this video, I'll be describing the architecture of the EveCore computer. I'll describe the registers and introduce and go over all the machine level instructions. This video is part of a series that will show you how to build a computer core in System Verilog. In other videos in this series, we'll walk through the design of an EveCore processor, showing how to implement the core on a small FPGA. But today, we'll be focusing on what any assembly language programmer would need to know in order to program the EveCore. The first question to ask about any computer architecture is, what are the program visible registers? EveCore has 8-bit registers with the names A, B, C, D, X, Y, and M1 and M2. The EveCore is fundamentally an 8-bit architecture, so these registers are 8 bits, that is 1 byte, in size. In some of the instructions, we combine the X and the Y registers to form a 16-bit register, which is referred to as the XY register. Likewise, for some instructions, the M1 and M2 registers are combined to form a 16-bit register called M. In addition, we have a program counter, or PC, and a stack pointer, or SP, and these registers are 16 bits in size. We also have 4 condition code registers, which capture the outcome of the ALU operations, and these are the carry bit, the sign bit, the 0 bit, and the overflow bit. Memory is byte addressable and begins at address 0, and can be as much as 64 kilobytes in size, although some implementations will have less than 64K of memory. Execution always begins at location 0, and so programs are loaded into low memory. And the stack grows downward, so the stack is usually located at the very top of memory. Since memory can be up to 64 kilobytes in size, addresses are always 16 bits, that is 2 bytes in size. We have a number of instructions that access memory directly, including the load and store instructions, and instructions that access the stack, including push, pop, call, and return. And we have this load code instruction, which is a variation of the load instructions. The EveCore architecture was designed so that it can be implemented using either the von Neumann approach or the Harvard approach. In a von Neumann computer, there's a single unified memory that holds both program and data, while in a Harvard computer, the program and data memories are separate. Often, the program is stored in read-only flash memory. Most of the previously mentioned instructions operate on the data memory, but the load code instruction is provided in order to be able to read from the program or flash memory. In the rest of this video, I'm going to be describing each of the EveCore instructions. Let's begin with the register move instruction. Every instruction begins with an 8-bit opcode, and in the case of the register move instruction, there's nothing beyond the opcode. All of the information is encoded directly in the opcode itself. So we have a source and a destination register, and these are encoded with 3-bit fields according to the expected encoding of the registers. For each of the instructions, I'm giving an example of how it would be coded in assembly language. The EveCore assembly language is a bit novel, and it may look a little weird to programmers who are used to traditional legacy assembly languages, but the goal with the EveCore approach is to make assembly code a little bit more human readable. Don't worry, we still have instructions written in the usual way with 1 instruction per line. Next, let's look at the move immediate instruction. The 8-bit opcode is followed by an 8-bit immediate value, which will be moved into one of the 8-bit registers as determined by this 3-bit field. Here we see an example of how this instruction would be encoded in assembly language. The immediate value can be expressed in all the usual ways, which should look pretty familiar to existing assembly language programmers. Here's the load instruction, which is a 3-byte instruction. The opcode is followed by a 16-bit address. A byte will be fetched from memory and then moved into the indicated register. EveCore is a big Indian computer, so the programmer doesn't have to worry about byte reordering, which, to be quite honest, drives me crazy. Anyway, in the assembly code, brackets are used to indicate that an instruction accesses memory. In general, the brackets serve as a visual cue to the programmer that memory is being touched. Here, the brackets also help differentiate between this instruction and a move immediate instruction. Here's the store instruction, which is similar, except that the byte is being moved from a register into memory. In the assembly code example, we see that the address can be specified symbolically, as is usually the case with assembly languages. We also have a variant of the load instruction called load M. It differs from the load instruction in that the address is computed as the sum of the 16-bit M register with a 16-bit immediate value. Remember that the M register is the pair of the M1 and M2 registers. It could be, for example, that M points to some structure in memory and that the immediate value is an offset to a field within that structure. Or this instruction could be used when we have a table or array. In that case, the 16-bit immediate value would be the address of the table or array in memory, and M would be an index into that table or array. In any case, with the load M instruction, the data is always moved into the A register. There's also a corresponding store M instruction, in which case a byte is moved always from the A register into an address that is the sum of the value of the M register with a 16-bit immediate value. Now here's this load code instruction that was mentioned earlier. It's encoded using a single 8-bit opcode, and it moves a byte from memory into the A register. The address comes from this 16-bit register XY, and it's always moved into the A register. If the EveCore is implemented with a Harvard architecture, then the byte is fetched from program or flash memory. If the implementation is a von Neumann architecture, well, this instruction provides a way to use the XY register as a pointer in addition to the load M instruction, which uses the M register as a pointer. The EveCore spec requires that the stack pointer register must be initialized to 0 upon reset, which would be appropriate whenever we want the stack to be located in high memory. We don't even need to bother initializing the stack pointer. Push instructions will always pre-decrement the stack top pointer, and with 0, this would result in a value of hex FFFF. This will cause the first push to store its data byte into the very most upper byte in the address space. By the way, if a particular implementation doesn't have the full 64 kilobytes of memory, then the upper bits of the stack pointer will be ignored. So as long as the size of the memory is a power of 2, this will still work fine. However, in some situations, we may want the stack somewhere else. And so for that, we have the load SP instruction, which simply loads the stack pointer register with the 16-bit immediate value that follows the opcode. Now we have the add 16 instruction, which performs a 16-bit addition. The result is stored either in the XY or the M register. The addition is the sum of the 16-bit immediate value with either the value that's in the XY register, or the value that's in the M register, or the value that's in the A register, which is treated as an unsigned value, or with 0. This instruction can be used in a number of ways. It can be used to initialize one of the 16-bit registers, or it can be used to increment or decrement one of these registers, or it can act as a move between one register and another register. Now we're ready to look at the ALU instructions. There are 16 different ALU instructions, the first of which is the logical AND instruction. All ALU instructions are 1 byte in length, so there's just an opcode byte. And in all ALU instructions, the two operands always come from the A and the B registers, and the result is always placed in the A register, which is sometimes referred to as the accumulator. Also, the ALU instructions modify the 4 condition code registers, so we can execute a conditional branch instruction after any ALU instruction. In addition to the logical AND, we also have logical OR and exclusive OR instructions, as well as a logical NOT or bitwise complement instruction. It just works on the accumulator, ignoring B. Here's the 8-bit addition instruction, and there's also a version of it that adds with carry, and that's useful for doing multi-byte addition. There's also an 8-bit subtraction instruction, as well as a version that does subtraction with borrow, and that's expressed like this in assembly language. The negation instruction will treat the value in the accumulator as a signed value and will negate it, and we also have a clear instruction which will move 0 into the accumulator. Next, let's look at the shift instructions. There are 4 shift instructions, 2 shift left and 2 shift right. All of the shift instructions will modify the carry flag to contain the bit that was shifted out. This version of the shift left instruction will shift a 0 in on the right side, while this version of the shift instruction will shift the previous value of the carry flag in on the right side. Here are the shift right instructions. This version of the instruction will shift a 0 in on the left or most significant end, while this shift right instruction will shift the previous value of the carry flag in on the left or most significant side. Here we have 2 instructions that will either increment the A register or decrement the A register, and this concludes our list of the 16 ALU instructions. But we've also got the compare instruction, which makes use of the arithmetic logic unit. It's expressed like this in assembly language, and what it does is it performs the A minus B computation without storing the result. It does, however, set the condition codes, so these can be tested in a subsequent conditional branch instruction. Here are the call and return instructions. The call instruction is a 3-byte instruction that contains a 16-bit target address of the function you want to call. In EveCore, all the addresses are a full 16 bits, and we don't have any PC relative addressing or anything like that, so they're just straight absolute addresses. The call instruction looks like this in assembly language, and there's a corresponding return instruction that's a single byte opcode. The call will push the return address on the stack, and of course the return instruction will pop that address and return to the location after the call instruction. The architecture also contains push and pop instructions. So just as you would expect, the push instruction takes the value that's in one of the 8-bit registers, as specified by this field here, and pushes it onto the in-memory stack, decrementing the stack pointer. The pop instruction will take the byte that's at the top of the stack and move it into the specified register. Now we come to the conditional branch instruction. It has a slightly unusual assembly language format. The if and the goto are keywords recognized by the assembler. The instruction is a 3-byte instruction, and it contains a 16-bit target address. We'll jump to that address if the condition is true. The condition to be tested is specified by this 4-bit field, and here are the possible combinations that can be used. And what we'll do is we'll test the condition code bits that were set by the previous ALU or compare instruction. We can test for things like equal or not equal, and we can also compare values. We can compare signed numbers and we can compare unsigned numbers. So here's how these unsigned comparisons are specified. We could also test the sign and the overflow flags directly. The conditional branch instruction is also used to implement unconditional jumps, and one of the 4-bit combinations is always true. the last combination of bits here is not used. We also have an unconditional jump instruction, which is called go to XY, and it's written like this. In this case, the target address to be jumped to is contained within the 16-bit XY register. This architecture also has a no-op instruction, which is just all zeros. Finally, we come to the last two instructions, the in and the out instructions. These are used for interfacing to I/O peripherals. All I/O is done by either writing to or reading from a set of so-called I/O registers. There's a space of up to 256 I/O registers, and each one is 1 byte in size. So we can specify the I/O register with an 8-bit field. So both the in and the out instructions are 2 bytes long, with the second byte being the identification of the I/O register you would like to read from or write to. So here's an example showing how we would write it in assembly language. Here we are sending to I/O register number 5 the value that's currently in the A register. And here's an example showing how we can read from an I/O register. In this case, again, it's register number 5, and we're moving a byte from the I/O register into the A register. So again, all I/O is done by either writing to one of these I/O registers with the out instruction or reading from an I/O register with the in instruction. Okay, that concludes our introduction and overview of the EveCore architecture. In other videos in this series, I describe how to implement this architecture in System Verilog for a small FPGA, where I hope to see you in the future. Thanks for watching. See you next time.